All right, hello everyone. This is our 20th session of the first section of USACO. We have only 3 units left. And today, this section is talking about the section 1.5, the first question, number triangles. Let me show the question first. Where's the question? Where's my browser? Wait. Yes, here it is. Okay, number triangles. Well, I briefly go through this question first. Consider a number of triangles shown below is like this. Write a program that calculates the highest sum of the numbers that can pass on route that start at top and end somewhere at the base. Here's the top, 7. Here's the base, 5 numbers. Each step can go either diagonally down to the left or diagonally down to the right. We later refer to left or right. So start from 7. You can either choose 3 or choose 8. 3 is left, 8 is right. If you have 3, then left and right. If you have 1, left and right. So go like this way. In the sample above, the routes 7 to 3 to 8, 7 to 5 produce highest sum, 30. 7 to 3 to 8 to 7 to 5, 30. And okay, here is the format. The format is you get the height of this triangle. The R is from 1 to 1,000, namely 5. 5. If you have 5, you have 5 lines to read. If you have 10 lines to read. Each subsequent line contains an integer from a particular row of the triangle. All the supplied integers are non-negative and no larger than 100. What this is telling you? This is telling you is if your height is 1,000, all right, and all the numbers are 100. So the largest number you are dealing with is 1,000 times 100. That means about 100,000. 100,000 can be stored in integers, so we don't have to care about any long data structures, any larger data structures. And output format is a single line contains the largest sum using travel space, which in this case is 30. One thing we need to know about this triangle is you can see the first line have only 1 number, the second line have only 2 numbers, third line is 3, fourth line is 4, fifth line is 5. So the nth line is going to have n numbers. And this will direct you to some special way to read the numbers. We'll talk about later. And secondly is about this format you are reading. You see in this triangle, you still have a left and right to talk about, but after you read these numbers in an array, you're going to have these formats. So the left is not left anymore. The left is actually the element down to previous element. For example, 3 is down to 7, so 3 is actually the left of 7, and 8 is right. The right is still preserved, but left is not. We need to take care of this is because by the first time I wrote this program around 3 or 4 years ago, I tried to build a data structure like this so I can read actually with left and right. And then I found out I'm wrong. This can also be very naturally represented. We just don't need to constrain ourselves as left and right. Okay, let's see the algorithm. I suppose everyone has already understand the question. Yes, this one. Okay, we have this triangle, and here's the path, and here is the input. We label 7 is layer 1, 3A layer 2, A10 layer 3, 2744 is layer 4, and last layer 5. This can explain clearer to the algorithm. And then now we need a data structure to record down all the numbers. Because our input here is from 1 to 1000, so we need at least AR plus 1 and R plus 1 size of array to store all these things. Bear in mind, in our data structure, about half of the array will not going to be used, but we still need to, well, store all those because we know we don't have so much choice on that. Here is a very special way to read all the data. We use I to control which level we're on, and we use J to control how many numbers we're on. So I is obviously from 1 to N, actually 1 to R, but I choose N here. It's okay, in this case the same. And J instead is not from 1 to N, it's from 1 to I. So you see, when I equals to 1, J is only going to iterate once. And if I equals to 2, J is going to be 1 and 2. If 3 is 1, J is going to be 1, 2, 3. I if it's 4 is 1, 2, 3, 4. So this is a beautiful way and very useful way, and you are going to see this a lot in many questions, how you read a triangle-like map or triangle-like array into your data structure. And read Aij is about layer I and the J's number. All right. One thing I need to tell you about is this question is officially the first dynamic question what we are facing. All right. Why we need dynamic programming? I don't want to waste our time to introduce you what is dynamic programming. But where I need to explain why we need dynamic programming. We used to have these two fundamental search techniques, DFS and BFS. But there is a problem with DFS and BFS, even though they can travel to all the states of their searching state, but the problem is they cannot memorize anything. That means when they proceed, they don't really care about previous days. And because they don't memorize, so for certain problems need some help with previous search states, DFS and BFS going to take a long to try to search it again, to combine them again. So you will find yourself with a lot of states you need to search on a very huge tree. The advantage of the dynamic programming is it restores all the travel solution which can be used in future. So we can quickly form a solution for it, for the current state based on the previous search result. And there is a nature of the dynamic programming. Dynamic programming is always have this property. It's like if I have to solve one problem, maybe I should solve the sub-problem first. Or if I have several states, stage 1, stage 2, stage 3, stage 4, if I want to solve the stage 4 problem, I need to solve first 3 stages first. And this gives us a lot of advantage. It's like, okay, now I'm going to solve the stage 4, and I have all the possibility solution of previous 3 stages. So maybe the stage 4 is only a small little update of previous state of previous solution. And previous solution, because we already stored those, so I can call them in O1. That means one operation, and then add something. So the whole algorithm become linear or polynomial, and instead of that is exponential. All right. But there is a disadvantage of the DFS of the dynamic programming. Is the most naive dynamic programming will actually cost you a lot of space. But a lot of space from you store all the states, of course. All these states, so all these states cost a lot of space. Therefore, when we try to optimize any dynamic programming, usually we are taking advantage of the space. Usually, we are going to design a more smart architecture of our data structure to store the same amount of information but with less array we're using or less dimension we're using. All right. Now I can officially introduce you this solution. I have a f, same dimension as triangle. It will record all solution to each number in number triangle. What does that mean? Okay, our solution, our goal is to find a path from 7 to the base. But instead of from 7 to the base, we calculate 3 to the base, maximum, and 8 to the base, the maximum. And then once we get these two solutions, we just need to add on, okay, which one is larger, and I can plus 7, and that is my solution. And in order to find the base 3, the solution from 3, we need to find a solution from 8 and from 1, and we compare, and we find the larger one, and then we add 3, and that forms solution 3, and up to the bottom. And you see, this is the beautiful of this solution. The bottom is you don't need to have any choice. 4 to the base is 4 because 4 is already the base. 5 to the base is 5. 2 to the base is 2. 6 to the base is 6. And lastly, 5 is 5. So, and then when you try to form this solution, you will see, okay, which one is larger, 4 and 5? 5 is larger. So this one, the solution is 7. 2 to the base is 7, and 7, 5 and 2, 5 is larger, 12, and here is 12. Okay, 12 larger than 7. So 8 to the base is 8 plus 12 is 20, and so on and so forth. So here we have a sub problem. If we want to get the solution from layer n, any layer, we need to solve layer plus 1 first. In order to form this layer solution, we need to calculate this layer first. And then we have two choices, either go left or go right. The left is my real left. Left is, in our data structure, is at the bottom. Right below that main. Fi plus 1j is, for example, if I search on this one, this is the left. We can see here 1 left is 7. I want to know this solution plus the one I'm searching is larger, or the right, this solution plus this one is larger. So I have two solutions, we compare them, and we choose the bigger one, and now we have the solution for this element. And finally, of course, because Fij means the maximal pass from Aij, and I should tell you this is the cost. We record the cost. So therefore, F11 him is a solution, and this as simple as this. Let's see the code. All right. IO doesn't matter. N is questions are read the data, just as I said, from I to N and I to I, and I to N and 1 to N and 1 to I. You have this, and then I define a function called find path. This will return me a real value, integer, so I just output it. Okay, here's the dynamic programming happened. First of all, we form the base. Okay, the nth layer, from the nth layer, the solution is obviously the number itself. So Fni, maybe let me copy the whole thing here. All right. Fni equals Ani. This is Ani. Fni is equal to them. Obviously, they are at the bottom, and the maximal path is themselves. All right, and then from n-1, from layer 4 up to layer 1, we search, and we search also from 1 to I, because we know the nth layer always have n numbers. And then we start to compare. For example, I start with this one. I compare larger than 5 or 5 larger than 4. If 4 n plus 1j is larger than 5, then 2, ij itself, 2 is going to be 4 plus 2. But else, obviously, 5 larger than 4. So we plus 5 and 2 together to get 7. And if 1 here is 1 here, once we search here, we need to find out F42 and F43 if they are, which one is larger. And the larger will get plus 1. And so on and so forth, we get to 7. And finally, we have F11. And F11 is our solution. All right? And I think, yes, this is all. I submit my question and see how awesome of this solution. GitHub, ACM, so I'm trying. You can see the largest case is 0.4 second, and this is definitely the 1000 case. But for else, it's less than 0.0 something. So it's very effectively, and you can try to use DFS to find a solution. It's possible. It's very possible. You can use also DFS to find a solution. Also possible, but you will see you are going to face the over time problem. The time is just solve this problem with the traditional searching techniques. Okay, I think that's it.